All right, continuing with section P.3, we're now moving into rationalizing denominators. So the process of rewriting a radical expression is as an equivalent expression in which the denominator is no longer contains a radical. So from our case is mostly a square root, is going to be called rationalizing the denominator. So this is part of our rules of simplifying is we do not like radicals in the denominator position. So if the denominator consists of the square root of a natural number that is not a perfect square, multiply the numerator and the denominator by the smallest number that produces the square root of a perfect square in the denominator. Okay. So if you are going to go on and you're going to end up taking pre-cal, we do a lot of simplifying radicals and rationalizing denominators. So all we need to do in this case is that I have the square root of 3. So if I have a square root of 3 times the square root of 3, well, that's just the square root of 3 times 3, which we see there would just leave us with a 3. So one of the ways that I can rationalize the denominator is that I'm just going to multiply the top and the bottom by square root of 3, because this is basically multiplying by 1. So we're going to get an equivalent fraction. So we end up with 5 times the square root of 3 on top. And we already saw square root of 3 times square root of 3 will just give us 3. It's rationalizing denominator. All right, so B, there's a little bit of a trick to it. So we have a 12 there, and 12 we know is 4 times 3. So we're not worrying about the top, we're just worrying about the denominator right now. Actually, there's another way to do that one. Let me do this first, and then I'll show you other ways we can do this. So that 12 will turn into a square root of 4 times 3, which we know that 4 is just, or square root of 4 is 2, so that's just 2 square root of 3. We also might want to do the same thing to the top, because if we have common factors, it will save us some trouble as well. So if we look at that 15 is just going to be 3 and 5. So we can break that up into a square root of 3 and a square root of 5. This really is just square root of 3 times square root of 5. And then on the bottom is just 2 square root of 3. Sometimes instead of multiplying by something, we could just break it down and maybe something can eliminate for us. And then we're just left with a square root of 3 over 2. All right, so we're going to go through some other methods of rationalizing denominators. These are just things to look for to help us rationalize. So just to go back on B, you also could have just done this. There's a couple of different ways we could have done this. Had you just broke it down like that and just worried about the denominator. Second, go back and fix that. Put that little extra sign in there. If you've done the square root of 15 and then you know that 12 is just 2 square root of 3. Another way to do this is that we're trying to find the smallest square root to multiply the top and bottom by. You could just multiply the top and bottom by square root of 3. And then you would have ended up with a 2 times 3 down here and a square root of 15 times 3. 45. End up with a square root of 45. So one of the things you always got to be careful of is that the square root of 45 can be broken down, because that's just 9 times 5. So just always be careful that if you have radicals, that you simplify them at some point. Because this isn't a simplified form. This isn't a simplified form, but when I break it down here, well, we got a 3 on top and a 6 on the bottom. Once again, we get square root of 5 over 2. So like I say, there's multiple ways to do it. Just certain things to watch out for definitely is that when you have radicals, especially ones that you think you can break down and simplify, do it. So we could have started first by breaking down that square root of 15, or you could try simplifying that square root of 45. But eventually you have to do that so we can get down to a simplified form. All right, so conjugates come up quite a bit in a few places, and you're going to see this again when we move into polynomials, um, finding multiplying polynomials, finding roots of polynomials will come back to conjugates. Um, and also when we talk about complex numbers, there's several kinds of conjugates out there. So expression that involves a sum and a difference of the same terms are called conjugates. So if a plus b, a minus b, these are conjugates of each other. So you'd see this if you had 3 minus 2. This conjugate would have to be 3 plus 2. So the only thing it changes is the sign in between them. So usually numbers like this we don't use it for. We typically use it for maybe something with a variable. X plus 5. Its conjugate would be x minus 5. In our case, like I said, we're going to use it with radicals. So you might see it with things like 2 plus square root of 3. Its conjugate would be 2 minus square root of 3. Or you might have 3 square root of 2 plus the square root of 7. Then its conjugate would be 3 square root of 2 minus square root of 7. Like I said, usually don't use it in cases like this. We use it with expressions like this that cannot be combined. So square root of a plus square root of b and square root of a minus square root of b are conjugates. If the denominator contains two terms with one or more square roots, we like to multiply the numerator and the denominator by the conjugate of the denominator. So we'll do this and we're going to see why it's going to work. So this goes to a rule that we're going to see again when we start talking about polynomials. Is that if I have a plus b times a minus b, what's going to happen is I'm just going to end up with an a squared minus a b squared. And the reason that happens is if I do my distribution, a times a is a squared, a times b is ab, b times a is plus ab, and b times b is minus b squared. What we see is that minus ab and plus ab cancel out, and I'm just left with a squared minus b squared. Now, if you're not sure what I did there with a FOIL, don't worry, we will cover a FOIL again. But I just want to bring up this property here. So when this applies to multiplying conjugates, or conjugates with radicals, what's going to do is that if I have a square root, it's going to make that square root disappear. So in this case, if I have a plus square root of b, a minus square root of b, well, you're going to get a squared, right? And then you're going to get the b squared. Or in their case, it's going to be square root of b squared. Turns into a squared minus b. So essentially what you're focusing on is that these two terms, you're going to get them squared, and there's going to be a difference between them. Okay, so when I go through this, I'm going to use this property, and then I'm going to distribute as well so you can see both ways this is working. Whatever clicks for you is going to click. All right, so we have 8 divided by 4 plus the square root of 5. So the conjugate of the denominator, because that's what we need, would end up being 4 minus square root of 5. So we're going to multiply the numerator by 4 minus square root of 5 and the denominator by 4 minus square root of 5. We're going to end up with 8 times 4 minus square root of 5 on top, and on the bottom we end up with 4 plus square root of 5 times 4 minus square root of 5. So remember, I have a plus square root of b, and I have a minus square root of b, or vice versa. That should give me a squared minus b. We should see this in the denominator in the end. I'm just going to do the step-by-step, doing distributive property first, and then I'll start skipping and using this property for b. So if I do the top, I have 8 times 4. 32. Sorry, my brain broke down there. Yeah. So we end up with 32 here, minus 8 times square root of 5. So I just distributed that 8 across. Distributive property here, 4 times 4 is 16. 4 times, well, let me leave it at 4 times 4 first. So 4 times 4, so 4 squared. And then we're going to have 4 times minus 4 times minus square root of 5. So that's minus 4 times square root of 5. Then we're going to have square root of 5 times 4, which will just be plus 4 square root of 5. And then we'll have square root of 5 times minus square root of 5, which will be minus square root of 5 squared, because we get it twice. I know it's weird looking on top. We'll end up with 32 minus 8 square root of 5. This cancels, and all I'm really left with here is 4 squared minus the square root of 5 squared. So 4 squared is just 16. And then square root of 5 squared should give us the 5. So remember that minus is on the outside. What's going to happen here is that we'll end up with 32 minus 8 square root of 5, and the bottom is just 16 minus 5. We're left with an 11 on the bottom. Now, sometimes at this step, you can simplify further. Because we're dividing by a prime, this is the end. We can't simplify any further. We can't reduce any of our numbers or fractions. All right, so for b, the conjugate for 2 minus square root of 7 is just 2 plus square root of 7. So this time, I'm not going to do this whole step here. But what I need to do is multiply the top and bottom by the conjugate. So multiply the top by 2 plus square root of 7, and the bottom by 2 plus square root of 7. So we have negative 3 times 2 plus square root of 7. And then on the bottom, we are going to have, so remember, it's going to be a squared. So the 2 squared minus, so square root of b times square root of b, which just leave me with just the b. So square root of negative 7 times square root of positive 7 should leave me with just the 7. So if I distribute across the top, negative 3 times 2 is negative 6. Negative 3 times square root of 7 is negative 3 times square root of 7. And then down here, we're going to have 4 minus 7. So we have minus 6 minus 3 square root of 7. It's going to be over minus 3. So this we're going to do further because everything's divisible by a 3. So if I factor out a negative 3 from the top, as you see, the step was pointless, but we don't always see that right away. We did do some extra steps here we didn't need. Like I said, if you don't see that, that's fine. That's why we're doing it this way. If I factor out a negative 3, that leaves me with a plus 2 here, plus square root of 7, divided by square root of 7. Those cancel, and we should have 2 plus square root of 7. Take a moment and pause and work on worksheet number 4 problems. These are just examples of what we can see happen. Bear in mind, like here, we got a square root of 21. So you might actually need to simplify that square root first before you even try to rationalize the denominator. And then this one, this is similar to B. It's just that the square root comes first. So just take a moment and think about how that would work. hopefully had a minute to work on that. So we have 2 square root of 3, and I would like to simplify this first. So I have a square root of 21, so that is just 7 times 3. So what we see here, we'd have 2 square root of 3, and if I broke that up, we'd have square root of 7 times square root of 3. So I can get rid of that square root of 3, and I'm just left with 2 over the square root of 7. Now from here, I want to get rid of that square root of 7 because it's in the denominator, so I just multiply the top and the bottom by the square root of 7. So I should be left with 2 square root of 7 over 7. And I know that may not look like it's simplified, but then that's simplified because we have a reduced fraction. We just have 2 and 7. I can't reduce that any further. And we have a rational number on the bottom, something that's not a radical. So here, the conjugate, we have 7 minus square root of 2, so we'd have to multiply by 7 plus square root of 2. And we do that to the top and the bottom. And notice you have that square root of 2 up here. That one's fine. We don't have to worry about that one. We can have square roots in the numerator. So what we're going to have is square root of 2 times 7 plus square root of 2 on top. And on bottom is 7 minus square root of 2, 7 plus square root of 2. Now remember, the property that we have is that if I have conjugates A plus B, A minus B, or even if I flipped it and it was the other way around, it's going to come out the same thing either way. What you get is that A squared minus the B squared. So my A, we'll do the denominator first. Our A is at 7, so we end up on the denominator. Sorry, not denominator. Yes, the denominator. We end up with the 7 squared. Then the square root of 2 is my B, so we end up with a B squared. So minus square root of 2 squared. I'm doing this way because it's going to help with C a little easier. On the top, if I distribute this, I have 7 square root of 2 plus square root of 2 times square root of 2, so that's square root of 2 squared. So we have 7 square root of 2 plus the square root of 2 squared, which is 2. And then here we have 49 minus the square root of 2, which is 2. So 7 square root of 2 plus 2 divided by 47. Okay, and like I said, C looks a little tricky, but it's the same idea as I have square root of 8 minus 1, so its conjugate would be square root of 8 plus 1. Like I said, it's just that operator in the center changes from subtraction to addition to subtraction, whatever you need. And we multiply the top and the bottom by square root of 8 plus 1. So negative 3 times square root of 8 plus 1. And then on the bottom, square root of 8 minus 1 times square root of 8 plus 1. If I distribute this, that is negative 3 square root of 8 minus 3. On the bottom, square root of 8 times square root of 8 is going to be 8 minus 1, square root of 8 squared is just going to be 8. And this, try it again, square root of 8 squared is 8. The square of 1 is just going to be 1. So we square the square root of 8 and we square the 1 and just make sure that's the difference. So we end up with negative 3 square root of 8, negative 3 over 7. Sorry about that. So if we do the nth root here, so the nth root of A equals B means that B to the power of n equals A. So for an example, if we have the square, so the cube root of 125, that's going to equal 5. That means 5 to the power of 3 should equal 125. So n is an index, and if n, the index, is an even number, then a is a non-negative number, and b is also a non-negative number. If n is odd, a and b can be any real number. So what that means is that, let's say I do the fourth root of 64. So the, sorry, I'm losing my voice a little bit here. Fourth root of 64. The fourth root of 64, oops, got the wrong number in there. Let's do 16, that will work in there. I was thinking of cube root. The fourth root of 16 would be 2. It's the only option there. However, if we go back here, we could have the cube root of 125 would give us 5, but we could also do the cube root of negative 125, which would give us negative 5. And that can happen because we know that if I take negative 5 and I raise it to the third power, that's a negative 5 times a negative 5 times a negative 5, so an odd amount of negatives, we're going to get a negative back. So when we have odd roots, we can do odd roots of negative numbers, but we can't do even roots of positive numbers, because in this case, what this means is that 2 to the power of 4 would be 16, but negative 2 to the power of 4, the only choice it has is 16. So just be aware that you, if you do a even root of an an even root of a negative number, it will be undefined. So the symbol here that we have this n radical sign is called a radical, and the expression is still called a radicand. So nothing's really changed there. Okay, so we want to find non-square roots here. So we're looking for the cube root of 27. So we need a number that when I cube it, whatever that mystery number is, it's going to give me 27. So you could try writing some things down. So like 2 cubed, that's just going to be 8. 3 cubed, that's going to be 27. So if I do that, I see, well, what's going to work here is 3. So my only answer is 3. Now, if I do the cube root of the square root of negative 27, and I accidentally gave this one away. In this case, same idea. Is like, I need a number that when I cube it gives me a negative 27. Well, if I have a negative 2 and I do the square, that's just going to be negative 2 times negative 2 times negative 2, right? So that'd give me negative 8. It's the same thing here. If I take negative 3 and I cube it, I should get negative 27. So my answer would be negative 3. All right. Same thing here. We need a number that when I raise it to the power of 4 gives me 16. And we just saw earlier that would be 2. And then here, I need a number that when I raise it to the power of 4 would give me negative 16, which doesn't exist in the real number. So my two choices are negative 2 or 2, and neither works. So this is undefined. Because just an example, if I have negative 2, negative 2, negative 2 times negative 2, I have an even number of negatives, and that cancels out. So if n is odd, then the nth root of a to the n will just be whatever a is. So if I was doing the fifth root of, say, 3 to the power of 5, I would get 3 back. But if I was doing the fifth root of -3 to the power of 5, I would get -3 back. So that only happens with odd roots. If n is even, then it's going to be just like when we had a square root. The nth root of a to the n is going to be the absolute value of a. So the reason is that, say I do the fourth root of, say, 5 to the power of 4. That's just going to stay 5. We're not going to worry that I can have another answer to it, because that's making sure we only keep that principal root. And then once again, if I did a fourth root of 5 to the power, -5 to the power of 4, what's going to happen is, because I'm going to have that -1 that's out from that 5 is going to be to the power of 4. That just turns into the square root of, or the fourth root of 5 to the power of 4, which once again would just give me that 5 back. So either way, what we should see back is just that 5. So quotient rule and product rule are going to work the same even with nth roots. You just have to be careful about that last one where the nth root of a to the n, sometimes it can be positive or negative, or sometimes it has to just be positive. This is the only place you're going to have to worry, but everything else here is the same. The nth root of a times b is the nth root of a times the nth root of b, and vice versa. The nth root of a times the nth root of b can be combined to the nth root of a times b. The nth root of a quotient b is the same as nth root of a quotient nth root of b. Once again, b can't be 0 because then it's undefined. And then the nth root of a over the nth root of b would just be equal to the nth root of a over b. We already saw this property already. So simplifying an nth root, like I said, not much has changed from what we were doing before. This time, to simplify any root, you can factor out any factor that has a power that matches the root. So if I have the third root of 72, and I broke down 72, I break down into 2 times 2 times 2 times 3 times 3. Now, because I'm looking for cubes, that's the only thing that I can use that property on, right? Because I need an nth root of a to the n just to get back that a. So we're going to have a cube root of 2 to the third times a cube root of 3 squared. These cancel and just leave the 2 behind, but this, I have to keep that cube root of the square root of 3 squared. And then because we don't like to have powers around that are not necessary, we'll just change that 3 squared into a 9. Let me pause this for a second. Sorry about that. That was a leftover from my old version of the slides, and this one. So if I'm looking for the cubed root of the square root of 40, or I want to simplify that. Well, let me see. What does 40 break down into? So if I take 40, I don't know if you know how to do factor trees, but 40, one of the things that splits into is I can split into a 4 and a 10. Well, 4 will split into a 2 and a 2, and 10 will split into a 2 and a 5. So 40 is just 2 times 2 times 2 times 5. So we got a cubed root, and we see we have 3 2s, so that is a 2 cubed times 5. So we're going to end up with the cubed root of 2 cubed times the cubed root of 5, leaving us with 2 cube root of 5. So that would be the simplified form. So here I have 125 over 27. We're doing a cube root. So we can break that up into a cubed root of 125 over the cubed root of 27. So this one's a little easier because the number I need to cube to get 125 is just 5. And the number I need to cube to get 27 is just 3. So the cube root of 125 is just 5, and the cube root of 127 is just 3. And now we've simplified it. And then for C, we're going to combine this because we have a cube root and a cube root. So as long as it's the same root, kind of like it's as long as it's the same exponent, then I can combine this into the cube root of 24x times 5x squared. So I'm going to leave that 5 times 24 because I'm going to break that down x cubed if I put the x's together. So we just need to bring down that 24. So let me do a factor tree again. Oh, well, 24. We can get a 2 and a 12. And then the 12 would break down into a 2 and a 6. And the 12 would break down into a 2 and a 3. So we end up with, there's that 5, and the 24 is going to break down to 2 times 2 times 2 times 3. So what we have here is the cubed root of 2 cubed x cubed. And then we're left with a 3 and a 5. So cubed root of 2 cubed, cubed root of x cubed, times the cubed root of 3 times x is going to leave us with a 2 times, so because n is odd, we're going to see here is that as long as n is odd, the nth root of x in the n, remember, brings me back the number it was inside, so we had a before, but if it's an x, we have the cube root of x cubed, leaves me with just the x, so I don't have to worry about an absolute value here. Times 3 times x. So this is just 2x cubed root of 15. Okay. So try on yourself, try it by yourself. So these are a little different. Last one, we're just using cube roots, but we have a 5th root and then we have a 4th root. Okay. No, this one's right. I was just checking. You have to take a moment with these ones. You might require a little bit of thinking on this, but like I said, just some examples, kind of start your thinking about how to do these and come back. All right, so we have a 5th root, a 5th root, and a 5th root, and it's all product. We can combine this all under the same 5th root. We'll have 6x times 8x squared times 18x squared. So we got the 6 and the 8, because I'm going to break these up, I'm going to leave them all like that. 6 times 8 times 18. And then we have x times x squared times x squared. That's going to give us x to the 5th, because the product of all those x's. So 6 is just 2 times 3. 8 is just 2 times 2 times 2. And 18 is going to be 2 times 3 times 3. Okay. So we see that we have 1, 2, 3, 4, 5 2's. So 2 to the 5th, we have x to the 5th, and then we have 1, 2, 3 3's. So 3 cubed. And we're doing a 5th root. Sorry, my 5 disappeared there. So we're going to do a 5th root of 2 to the 5th, a 5th root of x to the 5th, and then a 5th root of 3 cubed. So that's going to leave us with a 2x and a 5th root of 3 cubed, or 27. So for B, we have 2 out front, and then we're doing a 4th root of that 81. So that 81 is just going to be, if you didn't know that, if you take 3 to the power of 4, you would get 81. And then we have x to the 7th. X to the 7th is just x to the 4th times x to the 3rd. So I can break that down. Now on the bottom, we're doing a square root. And we're doing a square root of 32, the 3rd power. If you think about that, that 32 is just going to be 16. Let me break that down further. 2 times 2 times 2 times 2 times 3 times 2. No, sorry, times 3. It's like I got extra number here when I was trying to do this. There. This is just going to be 2 times 2 times 2 times 2 times 2 to the power of 3. All right, so make sure the right number of 2's there. So that's what 32 breaks down into. So here we got that 2, the 4th root of 3 to the 4th, the 4th root of x to the 4th, and a 4th root of x cubed. Then we're going to have, so remember, this is going to multiply 3 times. So we have 2 times 2 times 2 times 2 times 2. And then we have another group of 2's. 2 times 2 times 2 times 2 times 2. Then we have another group, 2 times 2 times 2 times 2 times 2. So we have 2 times 3 times x times the 4th power of x to the 3rd. And then we have 1, 2, well, 15, the square root of 2 to the 15. So we have 6x 4th root x to the 3rd on top. And then here, we have a square root of 2 to the 14 times 2. So the top hasn't changed at all. So as a reminder here, we are going to do a square root of this because this is an even power. And remember that the square root is just going to be 1/2. And we'll have a square root of 2 here. So this is going to be 6 to the x times the 4th root of x to the 3rd. As a reminder, like I said, if I had this, x actually changes to 2 to the 14th to the power 1/2, because square roots are power 1/2. So that's actually 2 to the 7th. So 2 to the 7th power times the square root of 2. And 2 to the power 7 is 128. So we got 128 to the power of 2, 6x times the 4th root of x cubed. 6 divided by 128, so both of those are divisible by 2, leaving me with 3. Oops, put this up here so we can see it. It's going to leave me with 3x times the fourth root of x cubed over d4, square root of 2. All right, at that point, we're not done because we got that square root of 2, so we have to multiply a square root of 2 and a square root of 2. So we end up with 3x square root of 2, fourth root, square root of x cubed over 64 times the square root of 2 times the square root of 2. So it's going to be 3x square root of 2. I'm going to put that in there. Let me put that down below it. Three x square root of 2, fourth root, square root of x to the power of 3. And then we'll have 64 times 2, so we'll be back to 128. There, we're finally done. And that was B. Believe it or not, I believe I got that out of your book. Okay. So the definition of 1 over n. So a to 1 over n is just the nth root of a. We explained that earlier. Furthermore, a to the power of negative 1 over n is just the power of 1 over a, or 1 over a to the power of 1 over n, which is just equal to 1 over the nth root of a. So what we're saying here is that if I have 27 to the power of 1/3, that is just the third root of 27. However, if I had 27 to the negative 1/3, that is just going to be 1 over the third root of 27. So in this case, we get 3, but in this one, we'd have 1 over 3. If I ask you for 25 to the power of 1/2, well, that is just 25 to the power, or square, the second root of 25, or basically the square root of 25, which is just 5. Remember, this negative is not under this 1/4. It's on the outside. So this is negative fourth root of 81. So this would be negative 3. And this is 27 to the negative, I always accidentally do this, the negative 1/3, which we already said would be 1 over the third root of 27. And the third root of 27 is just 3. So if I have a to the m over n, I can rewrite that as n square root of a to the m, or you might see this as well, n, sorry, my thing glitched, n nth root of a to the m. You can see one or the other, which is what I have here. So this is interchangeable. Furthermore, if I have a to the negative m over n, then that's just going to be a to the m over n, which is just, or 1 over a to the m over n, just 1 over the nth root of a to the m, or 1 over the nth root of a raised to the power of m. So if I have 27 to the power of 4 over 3, really what that's saying is that I have 27. And remember, these are basically multiplied together. So let me write again here. a to the m over n is just a to the m under the nth root, or is it just the nth root of a raised to the power of m? It doesn't matter which way it goes. N's on the bottom, is it going to be a cubed root of 27 raised to a power of 4? Or you could have said it is going to be the cubed root of 27 raised to the power of 4. You may want to change these depending on what the problem is, because here I would have to raise 27 to the power of 4 then do a cube root. If I look at it this way, well, I already know the cube root of 27 is just 3. So I have 3 to the 4. So this is just 81. If we do it the other way, we say that would be 27 to the power of 4. We would be doing the cubed root of 531,441. So this one I'd have to do all in my calculator to even make it work. Which then if I do the cube root of that, make sure it was going to work out right, we'd end up at that 81. So be able to interchange which we use can be useful for us. As we see, doing it this way, that made it easier. I did that one by hand quickly. That one I had to use my calculator for. So 32 to the power of 2 over 5. Like I said, that can be the fifth power of 32 raised to the power of 2. Fifth root of 32 is actually just 2. Because 2 to the power of 5 is 32. So this is 2 to the power of 2, so this is actually just 4. Or if we did it the other way, we'd be doing the fifth root of 32 squared. What is 32 squared? 32 times 32 would be 124. And if you do the fifth root of 1024, you would end up back with 4. All right, and our last worksheet problem. So we're just combining a lot of these rules. We have rules of exponents and all that stuff, and we're going to do the best we can of combining our exponents and trying to simplify these expressions with exponents. So take a moment and do your best attempt to simplify as best you can, and then we'll go through it. Okay, so what we're going to see here is that I have only the x has the square root, has the exponent on it. That's the only part that we have to worry about converting. So we have 2 times 5, that's 10, times x to the 4/3 times x 8/3. So because we have those rules of exponent, that is 10 times x, the same base, we just add the powers. 4/3 plus 8/3. So that's 10 to the x, and that is going to be 12/3. Of course, I write 14. 12/3 what the power is, so that is just 10x to the 4th. And that one I can't do any more with. So here you have a 9 to the power of 20, or 5 over 4, 9 to the power of 7 over 4. So we know same base. In this case, I just subtract the powers. So we end up with a 9 to the negative 2 over 4. So that's going to be 9 to negative 1/2. So we know this is just 1 over 9 to 1/2, which means this is just 1 over square root of 9, which is just 1 over 3.